we have with us Chayan Chatterjee, our very own Chayanda. And Chayanda did his BSc and MSc from Presidency University. He is currently in University of Western Australia. He joined University of Western Australia as a PhD student and currently is as a project student and currently is pursuing his PhD there. So today he will talk about listening to the cosmos. How do we detect and localize gravitational waves in real time? So without further delay, let us hear from Chayanda. Chayanda, please share.
Yeah, let me share my screen. Is it visible?
Yes, yes.
All right, okay. So thank you, Nobunita, for the kind introduction. And hello, everyone. First of all, thank you to all the organizers of the Presidency Physics Alumni Lecture Series for giving me the opportunity to present my work. And today I'm going to talk about real-time detection and localization of gravitational wave events. And I'm doing this work in collaboration with my supervisors, Professor Lin-Ching Wen, Professor Amita Hodakto, and Professor Kevin Benson. So this is a brief outline of my presentation. So first, I'm going to talk a bit about the background of gravitational waves. Now, I know there has recently been a lot of talks in Presidency about gravitational waves, including the very nice talk by Shomendra recently at Precision. So I'm not going to go into the details of what gravitational waves are. I'm just going to discuss the main idea behind it. And I'm going to mostly talk about how gravitational waves are detected online using from an online gravitational wave search pipeline. In particular, I'm going to talk about SPEAR pipeline, which is developed by current and past members of my research group at UwA. And then I'm going to talk about some of the data analysis challenges which are faced by these online search pipelines and how it can be mitigated. These challenges can be addressed by using machine learning algorithms. So in this lecture series itself, there has been some really good talks on machine learning from Orithruda and Atreo, I think, and there might be a few more. So I'm sure most of you already have some basic idea about machine learning by now. So I'm just going to highlight the main idea again behind machine learning. And next, I'm going to actually talk about my PhD project, which is gravitational wave localization using machine learning. So I don't actually work on this SPEAR pipeline, but I wanted to talk about it because I thought that I think the online detection is something that has not been discussed in the gravitational wave context in Presidency. So I'm going to discuss the methods that I use, the different models that I use for localization using machine learning. And I'm going to discuss the results that I get using my machine learning models. So I have results for two cases. The first is when I consider simulated gravitational wave signals injected in O2 noise or noise from LIGO's second observation run. And I also test my machine learning models on real data, which is the real LIGO data for the binary black hole events from O2, and also the very first gravitational wave event, which is GW150914. And finally, I'm going to conclude with some discussion and plans for the future. So gravitational waves, as you all know, they are propagating disturbance or ripples in space-time, which are caused by the acceleration of heavy compact objects like black holes or neutron stars. And they are detected by instruments called LIGO, or Laser Interferometer Gravitational Wave Observatory. And currently there are the first two detectors in operation was Hanford and Livingston in US, and then Virgo in Italy joined in 2017. And finally, towards the end of this year, during LIGO's third observation run, the Japanese effort Kagra joined the detection, online detection as well. And the sensitivity range of these detectors is the order of 10 Hertz to 10,000 Hertz, which is basically the frequency range within which LIGO, these ground-based detectors are sensitive to gravitational wave frequencies in this range. And the way LIGO detects gravitational waves is by using the method of laser interferometry, where so these are basically 4-kilometer long laser tunnels, and whenever there is a passing gravitational wave event, one of these arms gets slightly elongated and the other gets slightly shorter, and that creates an interference pattern in the detector, which is observed as a gravitational wave signal. So when there is no gravitational wave passing, the laser from these two arms, they are completely out of phase and they cancel each other, and there is no signal at the detector. But because of the slight elongation and contraction of the arms, we get a periodic constructive and destructive interference, which is observed as a gravitational wave signal in the detector. Now, how are these gravitational waves detected in real time? So at present, there are 5 gravitational wave search pipelines which are allowed to send out open public alerts. This means that whenever there is a gravitational wave detection, these 5 pipelines can send out alerts to the public and to other scientists, who can then do other follow-up observations from those triggers. So these 5 pipelines are SPEAR, GSTLAL, PyCBC, MBTA, and CWB. Of these 5, the first 4, SPEAR, GSTLAL, PyCBC, and MBTA, are CBC search pipelines, which means they search for gravitational waves from compact binary coalescence or gravitational waves from sources which like binary black holes and binary neutron stars. And finally, the last one, which is the CWB, is the burst pipeline, which means that it searches for unmodeled gravitational wave signals. So these burst sources are gravitational wave sources of unknown origin. So it might be a supernova explosion, it might be something else. We are not sure, but there are no analytic templates or analytics template signals for these gravitational waves from burst sources, which is why it is a different category altogether. Now, the method that these 4 CBC search pipelines use to detect gravitational waves from detector data is mass filtering. And in this method, we have simulated millions of gravitational wave templates. And these gravitational wave templates are cross-correlated with the data to identify potential gravitational wave candidates. And this plot here shows the SPEAR template bank. And as you can see here, the X and Y axes here represent the primary and secondary masses of the component masses. And these are the ranges of binary black holes and binary neutron star and neutron star black hole masses that we try to discover from the detector data. So mass filtering, like I mentioned, is cross-correlation of data with template, and both of which are whitened using the noise power spectral density. So when I say whitening, I mean, so the data has different frequencies, and all of these frequency components have different power. And they are, so in the process of whitening, we try to get a uniform spectrum from the data, because we try to make the spectrum flat, basically. So it is weighted by the noise power spectral density to get a uniform spectrum. And the result of this cross correlation is the signal to noise ratio that you can see here in this plot. So this is the SNR for GW170817 event, which is the very first binary neutron star event that was detected by LIGO. So this is a very sharp peak. And you can see here that this was a very loud event with a very high signal to noise ratio. So here is a short animation showing how the mass filtering happens. So this is the data, and it is cross-correlated with the template. And whenever there is an event, we get a very sharp peak there. So whenever we get a peak which crosses a certain threshold. So for example, right now for single detector events, if this peak is above 4, we consider it to be a potential gravitational wave candidate. And then we do other kind of tests to confirm whether it is really a gravitational wave event or whether it is some noise feature or something like that. So now let's talk about the SPEAR pipeline. So SPEAR stands for Summed Parallel Infinite Impulse Response. Now, Spear pipeline is different from other pipelines in the sense that it does time domain filtering as opposed to the other pipelines which does the filtering in the frequency domain. And the way it is done is by using these infinite impulse response filters, which is a kind of digital filter. And we use GPU acceleration for the filtering. So there are many GPU threads, and each of these GPU threads will have a certain IIR filter, which corresponds to a particular segment of the gravitational waveform. And the output of or the response of these filters, these IIR filters, are summed together in a coherent manner to get the waveform that we are trying to estimate from that we're trying to discover from the noise, from the data. And the advantage of using this approach is that it is much faster than the Fourier domain match filtering, because as far as I know, the Fourier domain filtering involves calculation, like the match filtering in chunks of frequency bands, and that takes much longer than this time domain filtering, which actually is very quick, very fast. Virtually, I think it takes about 0-second latency to get the match filtering result using the time domain filtering. And this is the filter output this is the filter output of the IIR filters. So yn is the output and xn is the input data. And here ak and bj represents the IIR filter coefficients, which sort of represents the phase and amplitudes of these filters. And if you notice here that we use a portion of the previous output as an input in the IIR filter, which goes on to show that this is a feedback loop basically. So this is now a recursive function, and this is why it's called infinite impulse response, because for a certain, let's say if we have just a peak as an input, just one value of 1 and all the rest are zeros, then we can actually get infinite responses from these filters. And the SNR output that we get from this time domain filtering is actually equivalent to the frequency domain match filtering that other pipelines observe. So here is a comparison of the SNR output for the GW170817 event. And you can see here that they agree pretty much quite well. There is some difference, but they are mostly equivalent to each other. And now let's talk about the different infrastructure that is involved in this online detection thing. So first we have the detector data, and then this data is packaged. So during this data packaging, there are certain data quality checks. So basically, if the data is corrupt or if it has noise or some features which may not be suitable for further analysis, then we veto that data. So if the data passes all the data quality checks, then it is passed to the data analysis pipelines, which are these GW search pipelines that I mentioned. And in these data analysis pipelines, a lot of things happen. So first we have gating. So gating means if there is extremely sharp noise features in the data, extremely sharp delta function like noise features in the data, then we remove that portion of the data. Also, if there's we whiten the data, then there's filtering, and from the filtering output we get SNRs, and then we calculate chi-squares. And from the SNRs and chi-squares, the Spear pipeline, we calculate a ranking statistic, which allows us to get an estimate of the false alarm probability. And this measure of the false alarm probability gives us allows us to assign a certain level of significance to a particular gravitational wave triggered. So this estimate of the false alarm would help us judge whether the trigger is actually coming from a real signal or whether this is noise. And when all of this is done, after we have confirmed the detection, this is passed to the localization pipeline, the online localization pipeline, which basically produces sky maps of the gravitational wave events. And the other pipeline is the classification pipeline, which tries to predict which basically tries to classify a certain gravitational wave candidate between three classes, either a binary black hole or binary neutron star or neutron star black holes. And after all of this is done, the pipeline sends out an alert to the public. So this entire process, it takes about something like 30 seconds to 5 minutes to send an alert after the data is obtained. And just the detection process itself takes about 18 seconds. Now, this brings me to my PhD project, which is rapid localization and real-time discovery of gravitational wave events using machine learning. Now, you might have noticed that since the beginning of my talk, I have been stressing on the time, on fast localization, fast detection, and stuff like that. And also, my PhD project is focused on rapid localization of events using machine learning. Now, you might wonder, why is that so? Why do we at all care about the speed so much? And the reason is there are certain gravitational wave events like merged binary neutron star mergers, which besides producing gravitational waves, can produce this very sharp, very strong energetic burst of radiation called short gamma ray burst. And these happen about 1 to 2 seconds after a binary neutron star merger. And the reason we care about speed is, as you can understand, if these flashes are seen 1 to 2 seconds after a merger, then we need to be able to detect and localize gravitational waves within that 1 to 2 second window. Otherwise, we are going to miss the electromagnetic counterparts observation. And it is very important to have accurate localization of gravitational waves so that we can actually observe these, we can actually warn electromagnetic telescopes which part of the sky to look at, so that we can observe these short gamma ray bursts. And these short gamma ray bursts, these electromagnetic observations actually gives us a lot of information about the compositions of neutron star, which is still a very big mystery because the neutron star equation of state is still largely unconstrained. So, oops, sorry. Sorry about that. So this observation happened for the first time on 17th of August 2017, when gravitational waves and electromagnetic waves were detected together for the first time. So here in the middle is a plot showing the frequency evolution of the gravitational wave signal. So this is the very clear chirp that you can see from the gravitational wave stream. Yes.
Sorry, could you please hide the taskbar from below?
Yeah, I'm trying to do that.
Otherwise, it's okay. It's okay. Please go.
Wait. I think it is a result of doing the full screen thing. I'm not sure how to hide it.
Okay, it's okay. Please go ahead.
Should I? Do you think this is better?
No, I think full screen was better.
Okay. Okay, let me know if you cannot see something, then I can maybe minimize this and show it to you.
Maybe you can try slideshow.
Slideshow. Getting the same thing.
Same thing. Okay, so maybe if I have something in the bottom of the slide which is not visible, maybe I can minimize, because I'm not sure.
Sure. Please go ahead.
Okay. So yes, and after the detection of the neutron star, about 1.7 seconds after the merger, there was a peak in the gamma ray count in Fermi and integral satellites, which was, and this was the very first coincident detection of gravitational waves and electromagnetic counterparts from the same source. So this was GW 17817, and this actually started a new era in multi-messenger astronomy. Of course, multi-messenger astronomy was always there for a really long time, because we always had cosmic rays and neutrinos along with electromagnetic rays. But this was the first time we have gravitational wave detection together with electromagnetic radiation. And like I mentioned, LIGO uses Bayesian inference methods to get the posteriors of the sky, posterior samples of the sky direction. And it has two different ways to do this. The online method takes about 8 seconds, like I mentioned earlier, and the offline, which is the optimal method, which is most accurate, can take anywhere between hours to days. And that is because it uses the full Bayesian inference technique using nested sampling, and it uses many more template banks than the online search pipelines. And also it searches for parameters over the entire 15-dimensional space of parameters that actually used to form a gravitational wave signal. And therefore it is extremely computationally expensive, and it takes a really long time. But however, if we use machine learning, the prediction time from a machine learning model is of the order of milliseconds. So that is extremely beneficial for multi-messenger astronomy efforts. And also, machine learning can be used for pre-merger localization, which is localization of gravitational wave sources before the actual merger. And this is something that LIGO and Virgo is currently working on, because they're really trying to push it forward for future observation runs. So I wanted to show these plots here. These are sky localization contours this is on the top here is GW170817 localization. And this is an interesting event which was reported earlier this year. And this may be the very first observation of electromagnetic counterpart from a binary black hole merger. Now, this goes on to show that localization is really important, and it may reveal a lot of interesting phenomena. Now, let us try and understand how localization is achieved in the first place. So let us take a look at this video. So let's imagine that this is Livingston and this is Hanford, and here is a gravitational wave passing through in this direction. Now, this dashed line represents the distance that the wave has to travel for a part of it to reach Livingston to Hanford. Now, since gravitational waves travel at the speed of light, it takes about 6.9 milliseconds for the wave to reach from Livingston to Hanford, which allows us to calculate this angle theta. And this theta angle gives us a ring of possible sky directions. Now, the gravitational wave detectors, Livingston and Hanford, they are most sensitive to waves which are perpendicular to the two arms of the interferometer. And the sensitivity drops off as the incidence angle deviates from the perpendicular. Also, because of the curvature of the Earth, there is slight amplitude and phase differences between the signals that are received at Livingston and Hanford. And this knowledge of the difference in the amplitude and phase at the two interferometers helps us to constrain the ring to smaller parts of the sky, as we can see here. So to repeat, the important information that we need for localization is the arrival time delays of the signals in different detectors and the amplitudes and the phases. So this method is called triangulation, and using this method, LIGO and Virgo is able to localize all the gravitational wave events. So this animation shows the sky localization contours of all the 36 events from the first half of LIGO's third observation run. And you can see here that these contours have various different kinds of sizes. So some of them are really small because they are very well constrained and they were detected by all three detectors together. And some of them have very large contours which are spread out all over the sky. And that's because only maybe 1 or 2 detectors were in operation during that time. So if you have 2 detectors, we get only a ring in the sky, just like we saw in the video in the previous slide. And if just 1 detector is in operation, then we basically cannot constrain the sky position at all, and we get contours all over the sky. So I wanted to talk a bit, I think I should minimize this slide a bit, yeah. So I wanted to talk a bit about antenna beam pattern. So the LIGO detectors, they have a certain sensitivity to gravitational wave signals. So we know that the gravitational waves have plus and cross polarization. And this is what the response or the antenna beam pattern of LIGO and Virgo look like for these two polarizations. And this is the average of the two. And as you can see here that it is a donut-like feature where every, at the top and bottom of the plane of the two arms of the interferometer, the instrument is most sensitive, and it is least sensitive at in the plane of the two arms. And if we project this on the sky, we get the features that look like this. So these bright spots are regions of high sensitivity, and these dark spots, which are they are called blind spots, and they are regions of very low sensitivity. Now, if there is a gravitational wave which is at the bright spot of two detector and in the dark spot of another detector, then it is not going to be visible in that detector, and it is going to be visible on the other two, like we can see here for this event, which is denoted by the star here. So for this event, only Hanford and Livingston will be able to detect the event, but not Virgo. But the interesting thing here is that although Virgo is unable to detect this event, it can still contribute to localization. And how? Let us take a look at this video to find out. So this is Hanford antenna beam pattern. By the way, this is the localization for GW17817. Okay, this is the triangulation for Hanford-Livingston in the time delay line, and this is the localization contour that we get from Hanford-Livingston. Now notice that the Virgo blind spot coincides with the time delay line of Hanford and Livingston. Now, if we do an amplitude consistency check across this region of the sky, we try to match the observed SNR with the SNR that we get in these regions, we find that there is an exact match in only a very small portion of the sky. So despite the fact that Virgo got very low SNR, it was virtually, Virgo was actually unable to detect it very well. But in spite of that, we get very good localization. I think this was around 28 square degrees in the sky. So this was a very good localization because of the fact that we knew that Virgo had a blind spot in this region, and we could remove that part of the sky and therefore get very good, very accurate localization. Now, so these are all the information that I need for localization. I need nothing else. I have my time delays, I have phase lags, I have amplitudes and SNR ratios, and I extract these features from simulated gravitational wave signals, and that forms my input feature vector for my machine learning model. So first I simulate these gravitational wave signals, and then I extract these features from the gravitational wave signals. And for my output, I try to predict which grid or which sector in the sky the gravitational wave is coming from. So I divide the sky into numerous sectors. I typically use 2048 sectors, and I try to predict which sector the gravitational wave is coming from. And for that, I use a neural network. So, so this neural network is I think it has already been discussed by Aritra, but so these are, this is a kind of algorithm which draws inspiration from how the neurons in our brain function. So we have an input layer, and we have one or more hidden layers, and finally we have an output layer. So it is the same as a neuron, where all the input information goes into in here, and then we get some certain output in the output layer. And this transformation or this propagation of information happens through all the layers of the neural network. So let us take a brief look at how a neural network is trained and how it basically learns to make accurate predictions. So let's imagine we have input xi here, and this is passed to the next layer here, next neuron, and associated with these arrows here are some weights and bias terms. So the weights are multiplied to the input vector, and some bias terms are added to it. And then the result that we get, which is Z, is passed through some nonlinear activation function. So I've minimized so that you can see it better. So this nonlinear activation function can be many different things. It can be a sigmoid function, it can be a hyperbolic tangent, or it can be a rectified linear unit. Any of the, or there can be some other kind of activation functions. And the reason we use this activation function is to introduce some nonlinearity in the model, so that the model is able to learn the non-linear features of the data. And finally, after all of this, all of these operations, which happens in all the layers of the model, we get some prediction in the output. And let's say that prediction is yi. And then this prediction is compared with the ground truth. So let's say that's y. And we basically calculate the error between the ground truths and the prediction. And the way the model is trained is by updating the weights and biases of the model to minimize this error between the ground truths and the prediction. And the way it is minimized is by, we calculate the partial derivative of the error with respect to the weights, and using these equations, we update the weight in each iteration of the training process. So this is an optimization problem, and it happens through iterative learning over many epochs. And finally, a model that is very well trained will have reached the global minima here. So this method is called gradient descent, where the weights and biases are continuously updated to ensure that the cost function reaches the global minima here. And the model that is able to reach the global minima will make very good predictions on unseen data that the model has not seen, that the model has not been trained on. So this is a rough idea about on how a neural network is trained. So this is the neural network model that I use. I have in my input features the arrival time delays, amplitude ratios, and phase differences, which I extract from simulated gravitational wave signals. And in the output, I have a probability distribution. So for 2048 sectors, I have 2048 probabilities, which corresponds to the probability of a gravitational wave to come from that sector in the sky. And this is the, this is the architecture of my model. So I have 200 nodes in each layer, and I have about 6 hidden layers. And for training, I have binary black hole, gravitational wave signals from binary black holes of masses between 30 and 80 solar mass, and SNR between 10 and 25. And I inject my signals in Gaussian noise, which is colored by the power spectral density of advanced LIGO, which basically means that the detectors have very high sensitivity, which actually is not true, which is not not very real. So this assumption that the signals are injected in Gaussian noise is a very simplistic assumption, because real noise is extremely non-stationary, and it has these very sharp noise artifacts called glitches. And whenever a machine learning model tries to learn anything from non-Gaussian data, it performs very poorly because of the non-stationary features in the data. So, but however, using the results, using signals injected in Gaussian noise, we are able to obtain these results. So for 2048 sectors, we tested our results for the 2 events, GW150914 and GW170823. And you can see here that we used, so we use, we get a 90% credible area of 312 square degree for this event. And B star, which is LIGO's online localization pipeline, had 610 square degrees. However, this is of course not a fair comparison, because we assume that we are injecting signals in Gaussian noise, which is not the real scenario. And the main advantage of this approach is that we are able to make this prediction in milliseconds using just 12 CPUs, which is orders of magnitude faster than any other technique. And the way we get these intervals, these contours, is by treating the machine learning probability distribution as a ranking statistic. And so we rank the sectors based on the probability that we get out of our model, and we are able to estimate these contours. Now, if we have signals injected in O2 noise, which is noise from the second observation run, we get very poor localization, as you can see here. And of course, the reason is the non-stationary nature of the noise, the glitches, and the poor Virgo sensitivity. So Virgo had extremely poor sensitivity during the second observation run, and that did not help in localization at all. So some improvements. First, we use HealPy to obtain equal area contours. So you might have noticed that my sectors towards the poles, if I have these rectangular or square sectors, towards the poles, the sectors have areas which are different from those near the equator. So the way to overcome this is by using heel-pick sectors, which was basically designed to obtain equal area pixelization of a sphere. So those of you here who work on cosmology might have heard of it or might have even used it. And this was actually specifically designed to work with CMB data. So I go on from rectangular sectors to heel-pick sectors. I pick sectors that I get out of this software called heel-picks. And the most important improvement that I was able to obtain was by using a new neural network called Denoising Autoencoder. And the job of this autoencoder is to remove the noise from strain data. So I have noisy data. I use a denoising autoencoder to remove the noise and get these pure waveforms out. And now let's talk a bit about the denoising autoencoder. So this is what the network basically looks like. So it consists of two parts, the encoder and the decoder. And the job of the encoder is to take the input feature or the input signal and reduce the dimension of the input data into a compressed representation, which is represented by this feature vector H. So the job of the encoder is to learn the essential features from the input vector and basically try to summarize that input vector into this hidden feature vector H. And the job of the decoder is to try and reconstruct the actual input from this hidden feature vector. However, for a denoising autoencoder, what it tries to do is it tries to reconstruct the original input, which is uncorrupted, from this reconstructed data. And the way it does this is by trying to minimize the reconstruction error between the original input, which is the pure signal uncorrupted by noise, and the output of the autoencoder, which is the prediction that we get at the end. So I use a denoising autoencoder network where my input is pure waveform injected in noise, and my output is the pure waveform that was originally injected in the noise. And for training, I use signals injected in Gaussian noise. I have about 100,000 samples. And for testing, I have two cases, signals injected in real noise and real O2 noise, and signals and also real LIGO data for some of the actual gravitational wave events that were observed. And the output of the autoencoder, which is the pure waveform that I'm able to obtain, is then passed on to the ANN for localization. So again, so the ANN here refers to the artificial neural network that I mentioned in the previous. So here is the pipeline of the localization. So first I have noisy gravitational wave signal, and then that is passed to the encoder part of the autoencoder. So for my encoder, I use a CNN, or a convolutional neural network. And this is a special kind of neural network which is designed for image classification. So it has convolutional kernels which convolve over the images. So let's say if this is an image, then it convolves over the input images, and it produces these feature vectors. And then we have some pooling layers which produces a dimension of these feature vectors. And using these steps, it basically tries to extract the essential features from the input signals, and we get a compressed representation from this signal. Is there any question? Let me quickly check the chat.
No, there are comments.
Oh, okay, fine. Okay. So this is the encoder that is actually extracting the features from my input signal, and I'm getting the compressed representation here. And the decoder part of the network, so the decoder part of the network is basically getting the denoised gravitational wave signal from this compressed representation. And for the decoder, I use another kind of neural network, which is called a bidirectional long short-term memory. And this kind of network, I'm not going into the detail of how this does its job, but it is mostly used for time series prediction. So let's say if there's a company and there are stock prices of that company for the last few months, then we can use an LSTM to maybe predict the stock price of the next month or something like that. So for time series prediction tasks, LSTMs are extremely helpful. And this is a special kind of LSTM network where because it is bidirectional, this means that we have the data moves. There are two LSTM channels. In one of the channels, the data is moving in the forward direction, and the other, the data is basically reversed. It's moving in the backward direction. So the model is basically learning from both past and future data, and is able to make better predictions than standard vanilla LSTMs. And after I get the denoised gravitational wave signal, I extract features from this clean waveforms and then pass it to the ANN, and I get very good localization on real data using this method, this combined approach. So first, let's discuss some of the denoising autoencoder results. So these are the results that we obtain using my autoencoder for injections in O2 noise. So in orange is the waveform that is reconstructed from the from noise, and in blue is the pure waveform. And as you can see here, that there is very good overlap between the pure waveform and the reconstructed output, even for low SNRs like 6 and 8. And this is calculated using the inner product between the reconstructed waveform and the pure waveform, and it is weighted by the power spectral density, and basically the time and phase corresponding to the maximum value of the overlap is, or which is maximized overlap, is what we calculate here. And as you can see here, we get good overlap for these binary black hole signals which are injected in O2 noise. And I've tested it over 4,000 samples, with 4,000 samples injected in real noise. And we can see here that for a range of SNRs, I get this maximized overlap. So for Hanford and Livingston, we get very high overlap for almost all of the events. But for Virgo, it is quite poor, and that again is because of the poor Virgo sensitivity during O2. And you can see here that almost all the events are lying between 0 and 5, SNR 0 and 5, and it is extremely difficult for the autoencoder to reconstruct the pure waveforms from such noisy signals. Now I'll talk a bit about the results that I get when I use the combined models, denoising autoencoder and ANN, for injections in O2 noise. So this plot here shows the searched area, which is basically defined as the area of the smallest contour that contains the true location of the gravitational wave event. So I calculate the histograms of the searched area for two different cases. The first is, okay, let me minimize this again. Okay, so for the first case, we have signals injected in Gaussian noise, and I do not use the autoencoder in this case. And for the second case, I have signals injected in real noise, and I use the autoencoder. And you can see here that for 4,000 samples and for SNR between 10 and 15, I get I compare my search areas and the 90% and the 50% areas. And the important thing to notice here is that I get greater than factor of 6 improvement in search area when I use the autoencoder, despite the fact that I have O2 noise. So it goes on to show the power of autoencoder when it comes to helping in localization. Now this is a PP plot, and again I compare for the same different cases, same cases. So the PP plot here shows what fraction of samples are in what confidence intervals. So ideally, it should follow a 45-degree line here. So 100% of the times, the 100% samples should lie in the 100% contour, which is the entire sky, and that's very logical. And 90% of the time, it should be within the 90% contour, and so on. So it should follow this straight line here. And you can see that using the combined models, I get a much greater fraction of samples within the 90% contour than if I just have signals injected in Gaussian noise without the autoencoder. So again, it goes on to show how helpful the autoencoder really is. Now, I'm going to describe the results that I obtained with real LIGO data for some of the actual events that LIGO had detected during the first and second observation runs. So this is the result for GW150914, the very first gravitational wave event. And here is the contour that I obtained using my machine learning model. And this was obtained in, of course, in milliseconds using my approach. And here inside, you can see this very thin contour, which is the LIGO's offline Bayesian parameter estimation contour. And it has a very much smaller area than I obtained, of course. But of course, the advantage that I have is that I'm much faster, because this result was obtained after months of calculation and processing. Also, Baystar, which was, if you remember, the online localization pipeline, it had a 90% area of 610 square degrees. So my aim would be to do better in terms of accuracy than Baystar, because we are already faster than Baystar, because Baystar still takes a few seconds to localize an event. However, my localization is of the order of sub-milliseconds. But the idea is to lower, get these 90% area to be much lower than Baystar. So this is GW1509. This was GW150914, and these are some of the other events from the second observation run. So you can see here that for all of these events, my contours, they sort of agree with the contours that parameter estimation results predict. So they have good overlap with parameter estimation contours. However, in terms of the accuracy or in terms of the 90% area, there is still work that needs to be done. And I'm trying to see whether I can improve this accuracy further. So these are 3 more events. So there were a total of 8 events, 8 binary black hole events from O2. Sorry, there were 7 binary black hole events from O2, and I have tested on data from all of those 7 events and compared with the parameter estimation results. So in conclusion, I'd like to mention that fast localization is important for multi-messenger astronomy. And as the detectors become more and more sensitive, there are going to be more and more detections, which means greater data analysis challenges. And the advantage that machine learning has over Bayesian inference is that it is orders of magnitude faster. And I have shown that neural networks, if we have the appropriate features, it can give very accurate sky localization. Also, denoising autoencoder helps further in improving the localization. In future, my plan is to apply these models on binary neutron stars and neutron star black hole sources, because they are the more interesting ones, because we have a chance of detecting electromagnetic counterparts from these sources. And also, we want to improve the localization accuracy further, maybe have finer sky resolution, more number of pixels. That would really help. Also, our long-term plan is to apply and implement these localization models in SPEAR. So this would be the first pipeline employing any machine learning model in an online search. So that is the future aim. So thank you.
Thank you so much, Chanda. So now we shall have questions. You can either raise your hand or write the question in the chat box. Well, Doipan has a question. Doipan, please unmute yourself.
Okay, am I audible?
Yeah.
Hello. Yeah, okay. Hi, Chayanda. So that was a very nice talk. So my question is regarding the pre-merger localization. So how do you get that? You just expand on it?
Right now, the pre-merger localization infrastructure has been tested for 2 pipelines, which is SPEAR and GSTLL. And the way SPEAR does that is by having chopped templates. So let me go back to the slide. So let's say this is the gravitational waveform, and for pre-merger detection or localization, we can have chopped templates, okay? And we basically do match filtering using these chopped templates and get the SNR peaks. Of course, as you go, as you consider earlier segments of the gravitational wave signal, like before, as you go to more negative, like from the merger region, the SNR peaks will be lower because these segments of the signal have lower SNR compared to the merger regions, which is why it's very difficult to actually do detection and localization from pre-merger because of the low SNRs. But if we have tested this infrastructure, and I think right now SPEAR can send out triggers for BNS signals 30 seconds before the merger. I'm not sure about GSTLL, but yeah, the way SPEAR does this is by having chopped templates and then doing the usual match filtering.
Okay, thanks.
Okay, next we have a question from RC sir.
Hi, Chayan, can you hear me?
Yes, sir.
Okay, so yeah, so it's a nice talk. Some of the slides was really nice, particularly the one that was showing the angle and the localization angle and so on. So I had a question, since you were working on sort of various pipelines to detect these as quickly as possible. So let's say if you have events where the typical frequencies are different. So for example, supermassive black holes, or even amongst error mass black holes, if the frequency of the gravitational wave frequency is somewhat different. Are these methods are independent of those kind of things? I mean, it can be sort of scaled to any frequency, or is there anything specific about the frequency domain?
Well, that depends on the template bank actually. So if you consider the template bank that Spear has right now, we do not consider like very high masses. So because it depends on the sensitivity of the detectors. So as the sensitivity improves, as we lower the frequency threshold, we will increase our chances of observing these very low frequency gravitational waves. And when that happens, we have to increase our template banks. We have to have more templates. So right now with the current infrastructure, Spear will not be able to detect any gravitational waves from supermassive black holes because it does not have the appropriate templates to do match filtering on it. But as in future observation runs, as the sensitivity improves, as the detectors become more sensitive to those kind of gravitational wave signals, then we have to increase our template banks to detect them.
So is there anything in the mathematics of this that has a bound on the frequency, or is it just it's easily scalable?
As far as I know, I think it's pretty easily scalable. It's just a matter of having the correct templates, I think.
Okay, thank you.
Yeah.
Okay, I think Achyuda had a question. Achyuda, can you unmute yourself?
Yes. So first of all, thank you, Chanda, for this extremely interesting talk. I actually have one question and maybe a small suggestion or comment. First of all, question in the denoising autoencoder. So you first use a convolutional network to get the feature map, and then you use a LSTM. I was wondering, for an LSTM to work, there must be a well-defined sequence. And what does a CNN always ensure that the output it gives, which is essentially some kind of a set of features, they are also in a sequential, they're also present in a sequential manner?
Well, so you're right. So basically, I'm not. So if you go back, if you consider the structure of the autoencoder, so the feature vector is actually a lower dimensional thing, right? So in any case, this lower dimensional feature vector will not contain the entire sequence of the full sequence of the waveform. And it is the job of the decoder to reconstruct the waveform, right? So this is almost like, I think, principal component analysis, where you have certain like some features which are essential, and you're making another network predict the full vector from those finite number of features.
Yes.
So yeah, I mean, I can make the I can maybe tune the CNN and check the weights of the CNN to see what exactly it is learning, and try and make it more coherent so that it looks like the waveform. But the idea is not that. The idea is to denoise it, right? Because in the input is I have the noisy signal, right? And it is trying to reconstruct the pure waveform at the end. So what it will basically learn is some features which are present both in the noisy signal as well as the pure signal, if that makes sense, and try to reconstruct the pure waveform from that. So yeah, so we are not exactly sure how the CNN is doing it, but if we maybe visualize the weights which we can do from the CNN, then we can get a better idea about what it is learning. But going by the results right now, it seems to be learning fine because it's giving me signals which have good overlap with the templates.
Right. Okay. Thank you. And maybe a small comment. So there's something called a Bayesian neural network.
Yeah.
And it is like one of kind of the standard problems that people do is triangulation. So have you tried?
Sorry, I couldn't
I am not
hear
aware
what
of.
you.
Sorry.
I couldn't get the word that you mentioned right now.
Sorry.
Triangulation.
Yes, exactly. Like
Okay,
they have this kind of very standard problems that they solve is like localization of a boat when there are three signals, like three lighthouses or something like that, which sounds very much like the problem you're trying to do in a different scale. So have you looked into this approach? Because like the standard thing that they do is using a Bayesian inference, and what you're trying to do is neural networks. So this is somewhere in between, and that can maybe give you some like best of both worlds kind of thing. Have you considered that?
Yeah, true. So right now, if I go back to my plots, so these samples, let's say this contour that the LIGO has obtained, this is from Bayesian inference, right? And I'm basically, but my probability is machine learning probabilities, and I'm sort of interpreting that as a probability distribution and getting the contours and stuff like that. But yes, in the long run, the idea would be if I can use a Bayesian neural network to estimate posterior samples, that would be really interesting because like I mentioned, I have a resolution problem already because I use a finite number of sectors, and right now each of my sector is 13 square degrees. Okay, so that is I'm already restricted by the size of the sectors. So if I can directly estimate the area and depth posteriors using a Bayesian neural network, then that would if I can able to get accurate predictions from it, then of course it can lower down, it can give me much better areas using that method. And there is just one paper right now, which one group who has worked on it, but they haven't used real data. I think right now I'm the only one who is working on localization with real data on machine learning. So yes, people are working on it, and down the line, I have plans to look at Bayesian neural networks as well. Yeah.
Thank you so much.
Yeah.
Well, SSR has a question, so please unmute yourself.
Hi, Chayan. Nice talk and nice work.
Thank you, sir.
So, I have one question. You were talking about the beam pattern of any detector, correct?
Yeah.
So I was wondering if you have some kind of beam pattern and you are using only one detector, then there will be a large uncertainty in the amplitude of the detection itself. Then how does it how do you actually localize?
So yeah, so we are not able to localize it at all. So what we obtain here, so let me go back to the plot. Yeah, so if we have one detector, we get the two blobs on the sky. That's all we observe, which is basically reflects the antenna beam pattern. So if I don't know whether I can play the GIF again.
Why can't it be in any other place with a much higher amplitude of the actual gravitational wave itself?
What do you mean by any other place? I'm sorry, I couldn't get you.
Means maybe in the not only the blind spot is very small region, but there
No,
are.
no, I'm not talking about the blind spot. Yeah, we get this bright spot. So if there is, let's say, if there is a signal which is coming from, let's say, some direction in the sky, and it is detected by only one detector, then we get this bright spot.
Bright spots as what?
As the
probability distribution of the
yes.
likelihood of the source, and there is no zero here, correct?
Yeah, exactly.
So it's a very large area.
Very large area, yeah. Which is why we are not able to have any constraint on the sky direction at all.
Okay, so you are not using only one data in the
No. I mean,
neuron.
I'm using. So when I compare with the O2 events, like during O2, most of the events were 2 detector events, and for those cases I used 2 detectors. And of all the published events, and I have not tested for O3 events yet, but there are some events in O3 which were actually 1 detector events, and of course they have very large sky areas and stuff like that. But for the 8 events that I have tested, they were either 2 detector or 3 detector events.
Okay,
And
so they are either 2 detector or 3 detector events.
Yeah.
Okay, thanks.
Okay, we have a question from Shomendra. He says, does this method work for cosmological distances? I mean, can the sky localization be done independent to the distance of the GW source?
Yeah, this is an interesting question. So for this method that I described, I have assumed that the gravitational wave has already been detected, okay? I'm not trying to actually detect the gravitational wave and do the localization. So first of all, the question that you're asking is a detection question, whether if the gravitational wave is very far away, whether the signals will be detected at all. Yeah, and it's true. If it is very far away, the signal to noise ratio will be very poor. And like I mentioned, if we have a trigger with SNR less than 4, then we actually not consider it to be a detection at all. So it is actually a matter of whether we are first able to detect it, and if we are able to detect it, how well are we able to actually get the time delays from those signals. Because like if I go back to the plot here, yeah, you can see here that Virgo had very poor sensitivity. What this means is that Virgo was not able to probe a large volume of the universe. It was able to probe a much smaller volume than Hanford and Livingston. So all the signals that were received at Virgo had very poor signal to noise ratio. And therefore, my autoencoder, because the SNR is very poor, they were mostly between 0 and 5, it is not able to give very good prediction, and therefore the localization would also be poor if I consider Virgo information. So yeah, I hope that answers the question.
Well, I think so too. Well, is there any other question? Yes, he says, thank you, Chanda. Well, if there is no more question, we can end our first session here and we can move to the interaction session now. I don't think there is any more question. Thank you very much, Chanda, for this interesting talk. And the next
Thank
session
you for
will
having
be
me.